modification, these drugs are more flexible. Fourth generation, fourth generation, I have one which we are calling trovafloxacin. Again, of importance is this group that is again fixed in all of them. Again, we have the floral group, so they have only changed now from the piperazine group. They have come up again, just like we have talked of the other drug, with another more. The complex is a bicyclic ring, complex bicyclic ring, and it was found to have activity. But of importance again, at position number 1, there is introduction of a difluorophenol ring. In all the others which had good activity, we were having a methoxy group at that position, or we were having the ether at that position, but you can see an introduction, but difluorophenol ring at that position. I want to believe, I have to confirm that you must be having a group. There might be some little problem there. Let me just confirm, because it's important that I give you the correct structure. I am of the impression that I've left out a group at position number 1. God, Jesus Christ. Yes, sorry, that structure is not correct. Yes. This structure is not correct. This should be shifted to floxacin. This nitrogen is free. Sorry, that nitrogen is free, and the whole of this group, the difluorophenol group, should be on this nitrogen at position number 1. So I repeat again, you remove the whole of this group, you shift it to this position there. So when we look at trovafloxacin, it has, again, it borrows from nalidixic acid, in that this is a pyridine. It's a pyridine ring. This is a pyridine ring for so for trovafloxacin, this is a pyridine ring, as you can see, all of us can see. And then I'm saying the whole of this group, please shift it to position number 1. So unlike the others that have either an ethyl group there at position number 1, all the ones with cyclopropyl ring at position number 1, this trovafloxacin has an N difluorophenol ring at that position. So that is just looking at the structures and just trying to analyze them to see the similarities and the differences. But we're going to look at those structures together. So then we can note that the dynamic approach towards optimization of antibacterial activity, how was that done? It was done in several ways. The essential features for... Hello, doc. Niko kwa class. Wacha nimalize. So the dynamic approach towards optimization of antibacterial activity included, we are noting that the essential features for improving lead compound of fluoroquinone class included a 4-oxo group is essential for the activity. So that 4-oxo group, and we have seen that in all the drugs, we are looking at what could be done to the lead molecule was I think it was, we said flumequine. It was flumequine. So what are the things that we must have? A 4-oxo group must be there. Reduction of the 2,3 double bond eliminates activity. Remember, at position 2,3 we had a double bond. It must be there for activity. Position 1, nitrogen in ring A. That one we have said it can have several structural modifications. The side chain attached to ring nitrogen significantly affects the potency of the drug. The earlier compounds are salicylic acid, pepimidic acid, norfloxacin, and rofloxacin, sinoxacin, and so on, had an ethyl group as a side chain at the nitrogen 1, and we saw that. So most of the original molecules had an ethyl group at that position, and we are saying that group at that position is very important in affecting the potency of the drug. And we have seen it can be changed to a cyclopropyl group. We have also seen it can be changed in the last drug, it can be changed into a difluorophenyl group with improvement of the potency of the drug. And that again, when I mentioned that, I'm only giving the various drugs. So this is the general structure. For them to qualify to be fluoroquinolones, they must have a fluorine at that position. This group can change. This group, as we have seen here, can change. There are the incidents where, like in ofloxacin, where this position 8 and position 1 has been linked to form a cyclic ring. There are those groups where you have an ethoxy group at that position. There are those groups where you have a nitrogen at that position. So we are saying therefore that R group can change. I'm calling it R8. I'm remembering the group as per the position. That is, so R8 can have different drug. In fact, can even put an X there. It can be a carbon, it can be a nitrogen, and R8 itself can change. It can even be a halogen. It can be a group which can join the two rings. R1 can change. We have said it can be an ethyl group. It can be a propyl group. It can be a difluorophenyl group with retention of activity. And now that's all we are saying, and we have given examples. So you can see that one, piperazine ring. You can see that one, ethyl group, as we have said, that change there. And you can see here, that's why we say we can even put an X there. You can see the change there is where the carbon has been replaced with a nitrogen with retention of activity. So again, you can see this is just the other way around. That's a cyclopropyl group. Again, you can see this one. This again is, if you look at this, peroxacin, a bit different from the others, because in this one, the alkyl group, this was initially an ethyl group, but it has been substituted with a fluorine. So we are also saying the substituent at position number 1 can be a halogenated ethyl group, again with retention of activity. If you look at everything else in that drug, it is quite similar. But again, if you look at that drug, this is supposed to be position number 8. You can see it has a fluoro group at that position with retention of activity. We are going to mention all those examples as we go along. Additional rings at position 3 and substituted piperazine rings position number. That cannot be position number 3. Why is it disappearing? Surely. Wrong here. This cannot be position 3. Oh, sorry. I see. So if you look again at this, I think they are looking at the piperazine ring, and it's not very clear. They are looking at the piperazine ring. Wow, it skips. Why is it misbehaving? So when we see those additional rings, what we are talking about is about. So it should be prime. When you look at the piperazine ring, you have that 1 prime, as I've said, 2 prime, 3 prime, 4 prime, 5 prime, 6 prime. So we're saying you can have substitution on the piperazine ring. I want to believe. Let's go back to the points that we see whether that makes sense. My good. Then I think we should change it when it is here. So additional rings. So unsubstituted, I think when these additional rings at position 3, we are talking about should be 3 prime or additional rings or additional substitutions. I think we should be talk about additional substitution on the piperazine ring. And you're saying when you have the unsubstituted piperazine rings, like in this in pipimedic acid, enofloxacin, enoxacin, and ciprofloxacin, which have shown good activity against gram-negative strain of viable bacteria. We are only saying that you could add a piperazine ring. As we have said, you can add a piperazine ring, but it's not at position number 3. It is at position number 7. At position number 7 of these drugs, you can add a piperazine ring. Drugs, the piperazine ring is unsubstituted, as we have said. But you can now, the next point, you can have substitution with the methyl group at position 3 prime or 4 prime. So make sure that this is prime, because the original numbers are 1, 2 on the nitrogen. So any other numbering will be prime. So at substitution the methyl group at position 3 prime or 4 prime of the piperazine rings again leads to improved pharmacokinetics. So we have levofloxacin and ofloxacin. So again, when we mention the drugs, just wanted to put it to run away again. As we had said, ofloxacin 1, 2, 3, 4, but it is 4 prime. So you can see our 4 prime position in ofloxacin has been substituted, and we need to understand surely when we do put an alkyl group at that position 4 prime of the piperazine ring, what are we doing? We are increasing the alkyl groups increase lipid solubility. And we have said these drugs start with gram negative. We are trying to improve gram positive. So when we do put methyl groups on the piperazine ring has 2 centers of polarity. When we add a methyl group, you increase the lipid solubility, you increase the penetration of this drug through the gram positive microorganism. So that indeed is very easily and well explained. And the same case applied to levofloxacin. As we have said again, it has that methyl group at position number 4 prime. If we look at sparfloxacin, position 1, 2, and 3, it has a sub 1, 2, and if you look at 1, 2, 3. So it also, when we look at sparfloxacin, it has 2 methyl substitutions at position 1 prime, 2 prime, 3 prime, 4 prime, and 5 prime. Again, those methyl substitutions are just to help us increase the gram negative, gram positive activity by increasing the lipid solubility. And we had mentioned that earlier. So we are saying that that is important in substitution the methyl group at position 3 prime or 4 prime of piperazine need to improve pharmacokinetics. We have levofloxacin and ofloxacin, whereby the methyl groups, it is leading to improved pharmacokinetics because one, also, when you put the methyl group, the drug will have higher lipid solubility, better penetration of the lipid membranes, and then also when it gets into the cell and gets into the microorganism, it will have better penetration of the gram-positive microorganisms, and of course giving you better activity. Because when we are looking at these drugs, remember first we are looking at them general. The quinolones, you must first study them as general antibiotics, even as consider that they can be used for management of TB. The other unusual type of the side chain at position 7 is a bicyclic ring system, such as in trovafloxacin and moxifloxacin. Again, remember, we did mention these drugs at that position number 7. They do not have a piperazine ring, but they have a more complex bicyclic ring, and it was found still to increase their lipid solubility and increase their spectrum of activity, because they are now covering more gram-positive bacteria than the other drugs. Nalidixic acid and sosacin contain, as we had said, a pyridyl ring. So in the basic drugs, they had the pyridyl ring as our in that particular ring, and they, of course, nalidixic acid, as we did mention, had a methyl group at that position. Stereochemistry, the stereochemistry of methyl group, the third ring in the third ring of, or the stereochemistry of the methyl group in the third ring of ofloxacin exhibits a significant effect on the antibacterial activity. The S enantiomer is significantly more potent than the R enantiomer and is rather more water soluble than the ring. Saying, when we look at those drugs, remember I did mention, if you look at the drug of ofloxacin, levofloxacin, they are tricyclic. They are not bicyclic, they are tricyclic, and we're going to look at that methyl group you're talking about, and the stereochemistry, the orientation of that methyl group is actually very important. The stereochemistry of that methyl group in the third ring exhibits significant effect on the antibacterial activity, and we are saying that we are saying, come on, we are saying that the S enantiomer has more activity than the R enantiomer. So let's go back. So we are looking, I think levofloxacin was better. Yes, we are looking at the levofloxacin, and we did mention that for levofloxacin, nitrogen 1 and position 8 are joined by this group. This is a group. This is the methyl group we are referring to. And you can see it carries an alpha orientation. And in carrying an alpha orientation, it gives us the S enantiomer. And the S enantiomer is found to have more activity than the R enantiomer. So again, stereochemistry, we are familiar with stereochemistry, and I believe we are able to understand that concept, even for levofloxacin and ofloxacin. So physical chemical, so stereochemistry is important for that particular drug, and that is why we talked about levofloxacin. Levofloxacin. So we are saying levofloxacin is the S enantiomer, and definitely the levo S enantiomer as compared to the R enantiomer, which has much lower activity. So the R enantiomer is the dextro enantiomer, the S enantiomer is the levo enantiomer. That is why levofloxacin is in higher generation than ofloxacin. One being a racemate mixture, the other one being the pure enantiomer. Physical chemical properties: the quinolones show amphoteric nature due to the presence of both basic, that is a tertiary nitrogen. Where is the tertiary nitrogen found? Of course, the tertiary nitrogen will be found especially for those ones with a piperazine ring. The quinolones show amphoteric nature due to the presence of both basic, that is a tertiary nitrogen, and the acidic carboxylic acid groups in their pharmacophore. So amphoteric in nature means they can react both with acids and also react with bases. Their solubility is low, except between pH 6 to 8, and are prone to precipitation under more acidic conditions. So if you increase the acidity, that means they are weak acids. They are weak acids because of the carboxylic. Remember, carboxylic acids, drugs that have the carboxylic group or carboxylate ion are weak acids. So if you put them in strong acids, they will be precipitated. Their solubility will be decreased in acidic media, but it will be increased in basic media. Of course, if you put them in acidic media, they'll be precipitated, and that, of course, will have a problem with their bioavailability. So that is important. Amphoteric in nature, their solubility is influenced, is pH dependent. So therefore, that means these drugs, when you are formulating them, then it means you must buffer them so that they are within the pH that is necessary required for absorption. Their solubility is low except between pH 6 to 8 and are prone to precipitation under more acidic conditions. Due to poor water solubility, crystalluria as an adverse effect has been observed. What we are saying is that when you have drugs that have poor water solubility, when they get into the kidneys, especially depending on the pH, like especially if the pH, the pH of urine is acidic. The pH of urine is around 6 as compared to the pH of the body, which is 7.4. So as you get into the kidneys and the urine, the pH comes down. So that is the urine is weakly acidic. These drugs are weak acids. They will be precipitated in acidic media. If that does happen, then you can have crystals or urea, which can be a dangerous condition. And therefore, more often than not, for such drugs, you are also told to take them with a lot of water. Take them with a lot of water to have to improve on their solubility. So those are the general characteristics of the quinolones: poor water solubility, crystalluria, pH, their solubility being pH dependent, amphoteric in nature. And these are things that all of by now we are masters because we have done them for different drugs. So now we can comfortably look at structure activity relationship. And as we've always done, we will move from point one to from position one all the way to position number 8. I'm happy drugs work. I took a tablet of cetirizine and it has really helped me out. It has really helped me out. My flu was very bad in the morning. So drugs do work. So we are looking at position one. And we have already mentioned, again, we are only doing a summary of what we have discussed. So we're looking at position one, and this is the N1 substituent. We are calling it, that is position one. And at that position number one, we have a nitrogen, and that is why we are calling it an N1. And this is just a summary. We have said it can be an ethyl group. The examples: norfloxacin, lomefloxacin, and enoxacin. Try and draw as many structures as possible. But for in this one of the very good examples is norfloxacin. We have also said it can be a cyclopropyl group. We have again ciprofloxacin, gatifloxacin, and sparsfloxacin, with, of course, improvement or increase in potency. Remember, we said when you change from ethyl to cyclopropyl, you increase the activity. We have also said it can be a difluorophenyl substituent, and we gave trovafloxacin as an example. And you can see that, of course, as we change the group, there is also, as we had said earlier, there is also an increase in generation because we are changing the spectrum of activity. We are improving on the penetration of gram-positive and also, of course, improving on the spectrum of activity. All have resulted in increased potency. So when you put a cyclopropyl group, you put a difluorophenyl group, all that structural modification of replacing if it was a hydrogen with these three groups has increased potency of the resultant quinolone. Addition of some small group at the ethyl. Remember, we have mentioned that also that ethyl group can be halogenated. We have said that ethyl group can be halogenated, as in fluoroxacin. We looked at fluoroxacin and we said fluoroxacin has CH2 fluorine. So addition of some small group at the ethyl as fluorine, as in case of fluoroxacin, results in overall improved activity against gram-positive bacteria. Remember the halogens. The halogens really improve on the lipid solubility. The halogens also decrease the rate of metabolism, because we do note that ethyl group, when put at that position, it can be subject to metabolism. So when you put a fluoro group, you decrease the metabolism of that alkyl group and you increase the lipid solubility. Once you increase the lipid solubility, you increase the ability of this drug to penetrate the lipid membranes and even to penetrate the gram-positive microorganisms. So that is of importance. So we have looked at position one, which groups can be there, how do they influence the activity? biological activity is influenced by the following factors from the N1 substituent: one, steric bulk; two, electronic pi donation; and ideal special effect. So we are saying that that group that comes in, it must meet some of the it must meet some specific conditions. In other words, or it cannot be too bulky. Cannot be too bulky. It must have the necessary bulkiness so that, or the optimal bulkiness, so that that molecule can still penetrate the receptor. It will bring in some electronic, or it will bring in some, either increase electron density or decrease electron density, or increase lipid solubility. It will, of course, as we have said, also introduce a special effect. So that group must be appropriate. It must be the right group, which, when it is the right group, one, it will allow that drug still to access the receptor without much of a problem. So that group can introduce differences or different effects. It can have an influence on this ideal spatial effect, which of course is the same as the steric bulk, and it can have an influence on the electron donation, or it can have an influence. When it has an influence on electron donation, remember, like we are talking about fluorine, does fluorine usually is an electron withdrawer. Fluorine is an electron withdrawer, and that's where we are saying it can have an influence on electron donation of the molecule. Introduction of a tert butyl group at nitrogen 1 produce quinolines with enhanced activity against gram-positive bacteria, but with minor reduction of activity against gram-negative bacteria. So they also tried a tert butyl. You see, all of them have an ethyl group, and you ask yourself, why could they try? And that's why you're saying there is the introduction of the steric effect. Steric effect. You cannot introduce a very huge group. So they tried a tert butyl, a a carbon CH3CH3. They retry a tert butyl. Usually it's a CH2 and then a carbon CH3CH3. They tried a tertiary butyl group, but I think this group was a bit too bulky. It did have enhanced gram-positive activity. Of course, it will enhance gram-positive activity because there is much increase in the lipid solubility, but it was found to have minor reduction of the gram-negative activity. So it was not optimal, and that is why you will not find drugs with that substituent. So that is an emphasizing on the points we have said, that the group must have the optimal steric effect. It must be of the right size. It must have the optimal steric effect. If it is too bulky, it will of course have an influence. Again, also, if it is too bulky, it will bring in a lot of lipid solubility, and it will compromise on the water solubility, and the drug will have reduced gram-negative activity. So that group must have the optimal properties that are required for both gram-positive and gram-negative activity. In general, the cyclopropyl group appears to be optimum for activities such as in ciprofloxacin, moxifloxacin, and sparfloxacin. So this, as we had said, the cyclopropyl group was found to be quite good, and therefore it has been repeated in several groups with retention of activity. Replacement of the cyclopropyl group of ciprofloxacin by an oxetane had increased gram-positive activity relative to ciprofloxacin. When we talk about the oxetane is like the beta. Remember the beta lactam ring. Remember the beta lactam ring? The beta lactam ring is a four-membered ring with a nitrogen. That is the beta lactam ring. An oxetane is the same, but the nitrogen is replaced with an oxygen. So an oxetane is whereby you have a four-membered ring, a four-membered heterocyclic ring with an oxygen, with three carbons and an oxygen. So we are only saying if you replace the cyclopropyl group by an oxetane, there was increased gram-positive activity, but definitely the oxetane will have its problems because of stability. Because you remember we did mention when you have we are cyclic ring, and of course with the heteroatom, that ring usually has a lot of instability, and therefore what you look at, what are the added advantages against the disadvantages. And if you, of course, you will have advantages, you will have disadvantages, and you see how they cancel each other out and you take the better one. So the cyclopropyl ring was still found to be better than octane ring, and no wonder most of the drugs do have the cyclopropyl ring rather than the octane ring.